Chapter 1, slides 60 to 66. Now we know how to look at a bond and determine through electronegativity if there is unequal sharing of electron density. We also have just covered what the molecular geometry is around a given atom. Is it tetrahedral? Is it trigonal pyramidal? Is it trigonal planar? Is it bent, linear? We are now going to work towards dipole moment and combine these two concepts in order to examine overall dipole moment. Let's begin with specific examples for geometry and charge. One of the ones that we're going to use a lot is methyl cations. That's when a carbon has 3 bonds and no lone pairs. What does that look like given what we've just learned about geometry? Well, if you have a carbon and it's got 3 bonds, CH3, and that's all you're given, just CH3. It has 3 steric electron domains. So its steric number is 3. So that means I want to use sp2, right? 1 part s, 2 part p. I'm going to use 3 of these sp2 orbitals to make each of the sigma bonds for the CH3. That is represented by each of the lines drawn towards the hydrogens for the C and the H. So each bond that is pointed to is representing an overlap, a sigma overlap, head-on overlap, between the sp2 orbital of the carbon and the unhybridized s orbital of the hydrogen. That's what makes up that bond. However, because I used 3 sp2 orbitals, remember I do have 1 unhybridized p orbital. Even though it's not filled, that unhybridized p orbital is still there and represented by that purple p lobe. It is empty, and the carbon does not have an octet. Therefore, its formal charge is +1. Now, if you don't look at that orbital because it's empty, just like we don't look at lone pairs, the overall shape for this CH3 cation is trigonal planar. And electrostatically, it is very, very blue because it is void of electrons, right? It doesn't have an excess of electrons. It's actually in need of electrons. A methyl radical looks very similar. It also has 3 steric clouds around it, and you do not count the 1 electron in the p orbital as its own domain. You have to have the 2. So a methyl radical and a methyl cation look very similar. However, their electrostatic diagram might be more green with a little hints of blue, right? Because it has a little bit more electron density. It's only really missing 1 electron towards its octet. Let's switch to the methyl anion. The methyl anion is a CH3 with a lone pair. Its steric number is no longer 3. The lone pair counts as another electron cloud, so its steric number is 4. So I'm going to use my 4 sp3 hybridized orbitals in order to create the best configuration around that carbon. So I orient it in an sp3 orientation, which is going to be tetrahedral. However, that lone pair, so you can see the overall geometry here is tetrahedral, but because the lone pair is not considered part of the geometry, it affects the geometry, but I erase it to see really what we're dealing with here, and we have a trigonal pyramid, trigonal pyramidal system for the overall geometry of this methyl anion. As as such, you can see that the electron density with that lone pair there is really showing the electron density is red in that area of that lone pair. So, what does this all mean? If I want to now look at an atom and its surrounding bonds and lone pairs and atoms and figure out what the dipole moment is for that specific system, I need to blend both what I know about bond electronegativity and what I know about geometry. And this is going to work very much like vector physics, okay? If you are drawing the dipole for the individual bonds, but have the atom oriented in its typical geometry, you can add and subtract the vectors to see what the overall dipole moment is. So if you start with CH2Cl2, the carbon has 4 for its steric number. It has 4 bonds. So it's oriented with 2 of the hydrogens and 2 of the chlorines in a tetrahedral fashion. Since the carbon does not have any lone pairs, it's all bonds, all 4 of them are bonds, then we see all 4 bonds, and so we're really truly dealing with this tetrahedral form. Now, carbon and hydrogen, as we'll see in this course, have a minimal difference in electronegativity. So, electronegativity difference of carbon versus hydrogen, it's practically nothing. So carbon and hydrogen really do not have a polar bond. Okay, it's very minimal. So it's negligible in the face of other atoms paired up with carbon. So the difference between carbon and chlorine on the periodic table and their difference in electronegativity is much greater. So we're only going to consider the really big differences. So let's just look at the carbon-chlorine bonds. If you look at them individually, you can see the dipole vector drawn, with carbon being more electropositive and chlorine being far greedier. So that's the direction the electrons are getting pulled. I do the same for the other chlorine-carbon bond. When I consider the shape, they're getting pulled equally in those 2 directions, but they're not 180 degrees from each other. They're 109 degrees from each other because of the tetrahedral shape. Therefore, the overall pull, when you add them, is an overall pull between them in the direction shown to the right. So that's your molecular dipole moment. It's interesting considering water. When people look at water, sometimes they might draw it like this. They can draw it in a very linear shape. If you look at the individual dipole vectors for water, they're equal and opposite. And so you would think that water wouldn't have a dipole moment, but it does. Why? Because water is not linear. You have to consider the geometry. We showed you in a previous slide that water, because of its lone pairs, have a steric number of 4, and everything's thus oriented in a very tetrahedral shape. But we don't see the lone pairs. And so the real geometry of water is bent. That's what we see. And that has a direct effect on the dipole moment for water because those vectors are not equal and opposite. They're not 180 degrees from each other. They're in fact about 109. Not exactly 109 as you saw, and I don't care that you memorize these little nuances, but roughly 109 degrees, but definitely not 180. So they're not going to cancel, the vectors aren't going to cancel one another out. They're going to be additive. And so the overall vector dipole moment for water would look something like the red arrow. So you can see it's really important to consider the bond electronegativity as a vector, and around a central atom, you have to consider its geometry to get the overall vector domain, right? So the dipole moment. If the vector is in one direction and one direction only, then the polarity of that system increases. There's only one vector and you don't have to split the difference. So if you only had chloromethane instead of dichloromethane, as in the previous case, we have a very polar system here. The carbon-chlorine is really the only polar bond. It's linear and it doesn't, or I should say the vector is only going in one direction. And the tetrahedral nature, those carbon hydrogens can be ignored because of the difference, the very minimal difference in their electronegativities. And so we're looking at one vector pulling in one direction, and that is a very polar molecule. We can see the same effects for ammonia. Despite nitrogen having the small vectors with the nitrogen and the hydrogens, the biggest vector is between the nitrogen and that lone pair. So the overall dipole moment can be written as a culmination of all those vectors going from left to right linearly. Here's water again. Again, oxygen and hydrogen have a dipole moment, and so does the oxygen lone pair. And when you take all those vectors in all the same, notice they're all flowing in the same direction. When you add them together, it's one big vector going from left to right. When you look at the carbon double bond oxygen, you can see that the carbon double bonded to the oxygen in one very large vector domain, and then the oxygen to the electrons all flowing in the same direction make even a larger dipole moment for this system. And likewise, and lastly with acetonitrile, the carbon to the nitrogen difference is shown by the vector from carbon plus to nitrogen partially minus. The nitrogen also has a linear in the same exact direction. So you look at that, you're not splitting the difference there. You have the nitrogen electron vector, and they're all additive in exactly the same way, which makes even a greater dipole moment. So, bringing it all together, let's have you practice some electron donating and electron withdrawing group abilities based on what you just learned about dipole moments. So what I want you to do is to look at each one of these systems, okay? Pretend that R is you, okay? R is you. I want you to figure out what that group is doing relative to you, being the R group, okay? Let me take, for instance, well, similar to the one that we just did. So if R is you, what we just looked at, I'm going to do this one with you down here. What we just saw was that carbon triple bond nitrogen has a very strong overall dipole moment going from carbon to nitrogen. That's the overall, because it's linear, and carbon nitrogen has a differential in its electronegativity, and it's all moving in one direction. It has an additive dipole moment for that system as shown. So if you are R, that dipole moment for that whole unit attached to you, what is that unit doing? Is it withdrawing electron density from you as indicated by the dipole moment, or is it donating electron density towards you given the dipole moment? Well, just look at the dipole moment arrow. It's going definitively away from you. So if you are, let's just say you're a biological system and you have that group off of you, that group is considered an electron withdrawing group. I don't care about you. I want to know whether the group attached to you is electron withdrawing or is it electron donating.